we can recompute this value anywhere. So we're going to recompute the value before it's used. This is called rematerialization. This eliminates the need to do a reload. Load goes away. And if there are no other uses of the spill value, the spill goes away. And the definition that's hoisted into the pre-header goes away as well. Guess what? We're back to before LLVM happened. No harm done. So this is what I talk about. The later pass can deal with optimization, aggressive optimization the earlier pass has done. So we make sure no customization happens. We want to take a step further. Notice we can only do rematerialization currently on very simple instructions. We can only deal with instructions that basically have no register operands. That's not ideal because we need additional information to decide when is a good time to do rematerialization. Let's talk about generalized rematerialization. Let's just suppose we have hoist a pick load of a global variable into a pre-header. We want now to rematerialize this before its uses. If we don't have availability information, we can do this pretty naively. That means rematerialize the load that gets the address of the global variable, then rematerialize the load to read actual value. But notice that's 2 loads before every use. That's worse than spilling. However, if you have the correct alias information and have correct availability information, we may notice, for example, the value of the global variable is available in the second use. That allows us to get rid of one of the loads and may make rematerialization profitable. So the key point here is not only do we need alias information to be able to code motion, loads, and anything that touch memory, we also need availability information to do really good rematerialization work. Unfortunately, that information is not quite yet available, so we don't do this yet. The last part of my talk will focus on the work we're doing right now and some of the work we are thinking about or have in the plan. What are the goals? Well, we want faster compile time and generate better code, and we want to make the compiler more maintainable and flexible. These are not conflicting goals. We can really do this. It's not easy, but that's our plan. First thing we want to look at is called strong fee elimination. Earlier, I talked about the fee elimination and how naive it is. This simple case illustrates the issue. We have a fee node with 2 incoming values. The current fee elimination insert a copy in each of the incoming basic block. With strong fee elimination, it takes advantage of dominated information and some other information to eliminate the copies that are unnecessary. It coalesces them ahead of time. This means less work for the coalescer. This is good for compile time. The next step we want to tackle, the next thing we want to tackle is called iterative splitting. Let's assume, well, we want to be able to split arbitrarily and iteratively. Let's assume we split the life interval or something at the loop boundary. Now let's assume the newly created life interval still require additional splitting because it's used in the whole loop. We can do the same thing we do right now. It's splitting the basic block boundaries. However, if there are multiple users in the same basic block, and the basic block itself is large enough, it may create more register pressure, but then we can spill in the intro basic block. Insert a reload before a number of users are somewhat close to each other. Then we can share the value of the reload. This is what we mean by iterative splitting. I think this has a great potential of dramatically improve our performance. We also want to tackle aggressive rematerialization, not just generalized rematerialization. Let's take a look at yet another example. In the we have hoisted a number of load address computation into the loop pre-header. We can rematerialize them here easily if we have the correct availability information if we know X, in this case, is available inside a loop. So this is rematerialization. It at least make sure we don't spill. But we can take a step further. We can apply additional optimization on this. We have recognized there are some potential sharing possibility here. There's a looping variant, IV, and there's X, which is available inside a loop and doesn't get changed. Then we can reassociate some code and enable even more sharing. These are the kind of things allow us to do very aggressive optimization in earlier phases. Finally, let's take a look at the backtracking and linear scan. We talk about linear scan. It's trying to maximize the use of physical register resources, and it has to spill when you run out of resource. However, to spill a value, that means we have to reload the value back into a register. And to spill something, that means we have to first compute the value, which go into a register before we store it. So this is something like a conflicting problem. And the way that linear scan deal with this is through backtracking. Again, our favorite hypothetical 3-register machine. V1, V2, V3 gets the 3 registers, no problem. V4 comes along and it conflicts with all three of them. We have to spill. The way it does is with backtracking. It picks V4 for spilling. It backtracks to the starting point of V3, break it up into multiple smaller life intervals. The first life interval gets R3 right away. Now we're on to V4 again. V4 is now no longer conflicting with R3, so it gets R3. The second part of the spilled life interval comes in. Unfortunately, it conflicts with V1, V2, and V4. So again, we need to spill. So we backtrack again to the top, to the starting point of V4, undoing the rest allocation there, split it, and this allows rest allocation to go to a completion. You notice the obvious problem. Backtracking means we are constantly undoing and redoing allocation we have already done. This is very bad for compile time. We want to add the ability to spill previously allocated life interval without having to backtrack. This means no more linear scan. We don't want to be allocating in a fixed order. We want to jump to any life interval and allocate for that life interval. We believe an iterative approach and using